Hey guys, today we're going to be looking at the second piece of section 3.1 from our textbook, picking up where we left off last time. In case you forgot, in class we were going over classical, also known as theoretical probability. So today we're picking up with what is called empirical probability, and this is also sometimes referred to as statistical, or, as I like to call it a lot, experimental, because it's based off of what actually occurred. In simple terms, it's actually found by taking the frequency of occurrence over the total number of trials, also referred to on your formula sheets as F over N. So basically it's the number of times that something did occur divided by the number of times we actually tried to have something occur. So it's sort of difficult to see what's going on until we actually get into an example. So example 1, finding empirical probability. An insurance company determines that in every 100 claims, 4 are fraudulent. What is the probability the next claim the company processes will be fraudulent? So what we're looking for are two things. The number of times that something did occur. We're trying to find the probability of a fraudulent claim. So we're looking for the number of times that something was fraudulent, which it tells us here 4 are fraudulent. So therefore that's my value of F. And I'm going to divide this by the total number of trials. So it is looking at 100 claims total. So my probability is actually 4 out of 100, the same as 1 out of 25. So essentially this is the same as about a 4% chance. Alright, so that's essentially, in a nutshell, that is empirical probability. It's what actually occurs based off what we tried to have happen. Now, this actually leads us right into the next piece, which is the law of large numbers. And this is simply stating, in other terms, that if I have a large number of trials, hopefully if I can write, large number of trials, it basically tells me that the empirical probability will approach the value of the classical probability. So what I like to refer to this is, if I was using flipping a coin, let's say we flip a coin. I know that I have a 50% chance of getting heads. Well, I could go through and could flip the coin 5 times. I'd get tails every single time. But what's going to happen if I flip that coin thousands and thousands of times? It's eventually going to get really, really close to that 50% mark. Right? If I only have 4 trials, it might not be anywhere close. If I have 4 million trials, it's going to be very, very close to that. So the law of large numbers simply says the empirical probability will approach the value of the classical probability. All right, so that's a lot of the basic terms that we actually have for different types of probabilities. And what I can actually do with this law of large numbers is actually go into this next example, where I'm actually able to take a frequency distribution, which actually shows my empirical probabilities, and I'm actually able to find classical probabilities based off of that. So it says I can take what actually happens and make it an actual probability, and actually think about the actual probability of something else happening from there. And it says you survey a sample of 1,000 employees at a company and record the age of each. The results are shown in the frequency distribution below. If you randomly select another employee, what is the probability their age will be between 15 and 24 years old? All right, so I want to find the probability that a person has an age, which is X, that's between 15 and 24 years old. So, based off of this, I'm still doing the probabilities the same way. The number of times that it occurs over the total. So, how many times did 15 to 24-year-olds occur? Right here, 54. So I have 54 over the total of 1,000. Right? So because of that, there's my probability, 54 out of 1,000. Now, of course, I can reduce this down, but going off of the fact that I currently do not have a calculator attached to my hand, I'm going to leave it just like that. It's going to break down to, I can say, at least 27 over 500. Probably not anything lower than that. If it does, that's great. You just let me know what it is, and maybe I'll give you an extra credit point. So that's example 2. So based off that, I know there's a 27 out of 500 chance that the next person I pick randomly will have an age between 15 and 24 years old. Now, we also have this other type of probability. Like, I always like to bring this one up, just so you guys are aware of this. This is what is called subjective probability. And this is where a lot of people think they know about probability, but they actually don't. Subjective probability is using one's knowledge to make an educated guess in the form of a probability. All right, so basically, I know a lot about my students. I could go through and say, well, based off of how they've currently done on all their tests up to this point, I believe that on the next test for Chapter 3, 87% of all my students will get a 60 or higher. All right, now, that's an educated guess. Do I actually know what's going to happen? No. I don't even have the data to back it up, but I'm able to make some sort of educated guess based off of what I feel is possible, based off the knowledge that I actually have. So subjective probabilities pop up a lot. The book likes to make sure you guys know what they are, so I want to make sure I go over those also. We also have here the range of probabilities rule, which is sort of silly, but it's important to know also. It simply tells me that all of my probabilities that I'm ever going to create, oops, I don't need that set of parentheses, are going to fall between two values. I know that probabilities have to be larger than or equal to 0, and they must be smaller than or equal to 1. Now, in both of these cases, 0 is the same as 0%, and 1 is, of course, the same as 100%. Right? So I know that all probabilities have to fall between 0 and 100%. I can't say, oh, there's a 227% chance that this person is going to pass a test, because that doesn't make sense. All right, it's going to be between 0 and 100%. All right. Now, we also have the other important thing that's really the last important piece in this entire section, which deals with complementary events. And I would recommend putting a nice big star next to this, because this is something we'll be using a lot here in Chapter 3. And Chapter 4 hits on it a lot. It saves us a lot of time with a lot of our problems if we understand complementary events. So I'm going to be making sure you guys are good to go with this a lot in class, so make sure you guys hit this home. Complementary events are essentially a list of all outcomes not included, we'll put it that way, in the original probability. And I'm also going to go through and put a formula here, as well as some notes. Normally, complementary events are seen as the probability of E prime. And it's usually written probability of E with an apostrophe that marks prime. So if you ever see something in mathematics with an apostrophe, it's essentially just considered prime. It just means it's another piece. So here, this is complementary events are the probability of E prime. So basically, if I have a probability of E, and I add to it the probability of E prime, it's going to equal 100%. So the complementary event of another event, if I add those two events together, it gives me 100%. So for example, the probability of E, I could say, is getting heads when you flip a coin. The complementary event, or the probability of E prime, is getting tails, right? Heads is the probability of the event. Therefore, the pieces that are not included is the probability of getting tails. So here we have example 3, finding the probability of complementary events. Using the frequency distribution and the results from example 2, what is the probability that a randomly selected employee is not between the ages of 15 and 24? Now, if I go back to example 2, I know that we had a probability of 27 over 500. Right? That is the probability of E. 27 over 500. Now, I want to know the probability of E prime. The probability they're not between 15 and 24. Right? So I know the probability of E plus the probability of E prime is going to equal 100%, which is in this case 500 over 500. So for me essentially to do this problem, I just need to figure out the probability of E prime. So what over 500, when added to 27 over 500, is equal to 500 over 500. So I simply just do the math. 500 minus 27. This is going to turn into 473. So therefore, the probability they're not between 15 and 24 is 473 over 500. That is the complementary event to the probability they're between 15 and 24. Right? Now there's another way to do this in case you're still saying, well, Mr. Smith, that doesn't quite make sense. What's going on here? Okay, so we can go back a couple slides here. I want to find the probability they're not between 15 and 24. So I can still use the same frequency distribution and just add up all of these probabilities here. This is going to add up and give me 946 over 1,000. And if you're not quite sure, this actually reduces down to 473 out of 500. Helpful if I can rate. Right? Which if you look is actually the same exact thing that we got right here. Right? So there's two ways to look at it. You can do it either way, but it's very important to actually understand this whole complementary event piece, and we'll be doing a lot more practice with this here in class when you guys get there tomorrow. Now, we also have the fundamental counting principle. I'm bringing this back up again to make sure we really have this hit home. Example 4. A probability experiment consists of tossing a coin and rolling a die. Use a tree diagram to find the probability of tossing tails and rolling an even. So, what we have is, I want to make a tree diagram. So basically, I'm going to have some events, probability of E. I'm going to have a whole bunch of little lines branching off of this. So that's essentially what I want to have done. So I want to go through, let's erase this, and start making my tree diagram. So based off of this, I want to find the probability of getting tails followed by an even. All right, so I want to get tails, then an even. So I have to flip a coin first. And I know that when I flip that coin, I have two possible outcomes. I can either have heads or tails, which that makes sense. It's a 50-50 chance of getting tails. And then from there, I still need to make sure I have the entire diagram. Even though I want to get tails first, I still need to complete everything. So I know that if I flip that coin and get heads, I then have to roll the die. It's a 6-sided die. And I have 6 outcomes on that 6-sided die. I can get 1, a 2, a 3, 4, 5, or 6. Same thing goes if I flip a coin and get tails. I still have 6 outcomes for that. 1, 2, 3, 4, 5, 6. I get a 1, a 2, 3, 4, 5, or 6. So I'm supposed to make a tree diagram, but mine never really look like trees. I just pretty much make them however I can to make the data that I need. And I want to find the probability of getting tails followed by an even. So I can just follow my tree diagram and see what information matches. All right, I want to get tails, so I have to go to here. Then I went even, so how many outcomes do I have that are actually tails followed by an even? Well, there's 1, 2, 3. So I have 3 desired outcomes over my total. So I go through and count how many total outcomes are actually possible. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so I have 3 over 12. And of course, you guys should know this reduces down to 1 over 4, the same as 25%. Now, we have one last example. This is an example that is actually like one of those summarizing everything we sort of have, putting everything back together using the fundamental counting principle. All right, we actually went over a problem like this before. Your school ID number consists of 5 digits, ranging from 0 to 9, and digits can be repeated. What is the probability of randomly selecting 5 numbers and having them be your student ID number? So this is just like your student lunch line number, right? 5 digits going from 0 to 9. We want to find the probability of randomly selecting 5 numbers from a hat and having it be your ID number. So I have 5 numbers total that I'm working with. And I want to find out first how many total ways I can actually select those numbers. So I'm looking here first at the total. So I go through and say, well, the numbers can be repeated. So here in this first place, I have the numbers 0 to 9, which is essentially the same as 10 digits. So I have 10 numbers that are possible for the first place. Now, so like I said, since they can be repeated, doesn't matter what value goes in that first place, I have 10 that I'm actually able to use in the second place. The third place has another 10 that are possible. Fourth place has another 10 that are possible. Fifth place has another 10 that are possible. From here, I just have to go through, use the fundamental counting principle. If I have 10 here, and here, 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 and here, I just multiply the number of options for each place. Oops, missing a digit. 100,000, all right? There's 100,000 different values that are actually possible for making these randomly selected 0 to 9 digits and getting 5 of those. Now, obviously, if my ID number, let's say my ID number is 1, 2, 3, 4, 5, how many ways is it possible for 1, 2, 3, 4, 5 to come up? Well, it goes in order, so therefore there's only one possible way. So my probability of selecting my ID number randomly from picking 5 digits is going to be 1, because there's only one way my ID number can come up out of this 100,000. Okay? All right, so that is essentially all the material we have for section, the rest of section 3.1. When we're in class, we will go through and actually finish up some information on this. Feel free to go through, look back over this material, familiarize yourself with it, because we'll be going over some questions. You'll probably see a warm-up problem or two, very similar to the last couple here that we did in the notes. And then we'll do some extra practice and really go into the complementary event stuff, because like I said, that is the big piece for this entire section 3.1 that we have left. Thanks for watching, and I'll see you guys in class.